So we were talking about cycloalkanes and how they have these different conformers and different shapes that they can take on, the boat and the chair, etc. And that brings us to a concept called Cis-Trans Isomerism. Remember, isomers are molecules that have the same number of atoms of each element, but they're just connected in different ways. And what we'll see in organic chemistry is that there are many different kinds of isomerism, many different ways in which these molecules can be the same and yet different. So cis-trans isomerism is also called geometric isomerism, and it's a form of stereo isomerism. So this has to do with orientation in space, not connectivity. And so there are two prefixes here, and they are from Latin. Cis is for the Latin meaning the same, and trans meaning across. So you think about a transatlantic airline flight that goes across the Atlantic, right? The Transamerica would be across America. So trans is across. And then cis, I have a good relationship with my sister, and if there was, a dispute or an argument or something, we would be on the same side. So sisters on the same side. So when we look, here are two isomers. This is the cis isomer, and this is the trans isomer. And the difference here is these methyl groups in blue. Here, these methyl groups are on the same side of the ring. They are cis. And here they are trans. They are across the ring from each other. And I brought you a little model. This is cyclopentane. You can see the ring is 5 carbons. I didn't put methyl groups on there. I put little, I guess it would be fluorine atoms, but the green balls. And we see here, like the one on the left, the green balls are on the same side of the ring. If you look at the ring as a plane, the green balls are on the same side. If I want this to convert to the other, I can try twisting and rotating, but I can't get it to make the one on the right unless I break bonds. If I take this one off and switch their points of attachment, then I get the trans version. And now the green ball is on top and on one side. One of the green is on top and one's below. But you can only go from one form to another by actually disconnecting, by breaking bonds. And that's what makes these isomers. They're not just conformers or different arrangements, configurations. They're actually different molecules. And that doesn't happen in normal alkanes because there's rotation around single bonds. But when you make a ring of it, then you lose the rotation. And so this is the cis version, and this is the trans version, and they do not interconnect. And if we look here, the boiling point is listed. The boiling point of the cis version cis isomer is 99, and the boiling point of the trans is 92. And that might not seem like a big difference, but these have the same molecular formula. And the difference is only in the position of that methyl group. So when we name these then, we follow the same pattern that we've been doing. This is cyclopentane because there are 5 carbons in a ring. So cyclopentane, we have 2 methyl groups, dimethyl. We call one of them on the 1 carbon, and then we number to give the other the lowest, which would be 2. So they're 1,2 dimethyl cyclopentane. But there's 2 possibilities for 1,2 dimethyl cyclopentane. You can have these be on the same side of the ring. This is cis, and that one is trans because they're on the opposite. And they do not interconvert. Any questions? So let's draw some structures. Let's draw 1,3-dibromocyclopentane. And when we're drawing structures like this, we're not going for accurate 3-dimensional structures or anything. We're just trying to show to whoever happens to look at it which would probably be you and me, and nobody else in the whole world cares to look at your homework. But and so we're just trying to show what's going on here. So cyclopentane will be a pentagon, 5 corners. 1, 3. Now you can put the 1 carbon anywhere you want. And it's going to be dibromo. So on the 1 carbon, we're going to have a bromine. And so that's 1. Let's put some numbers in here. Call this 1 and 2 and 3. And so on the 3rd carbon is the other bromine. Now, can you tell, are these on the same side of the ring, above, both above? Can you see that? I'm trying to indicate that they're both above the ring. So would this be the cis isomer or the trans? So this is the cis isomer. And the other possibility then, make another ring here, is to have one of these above and have the other one below. And that would be the trans isomer. So let's do this one. 1 chloro, 2 methyl, cyclopropane. So drawing structures from the names, it's usually best to start at the end of the name and work forwards to the beginning of the name. Just like when we write the names from the formulas, we always start with the end of the name. So propane is how many carbons? 3. So this is going to be a triangle. 1 chloro, 2 methyl. So those 2 groups are going to be on adjacent carbon atoms. And you can pick whichever one you want. I'm going to call this 1. So there's the chlorine. And 2 methyl, if we're going with the line structure, I can just draw a line going down. And this, we understand that at the end of this line is a carbon with 3 hydrogens on it. Is the one I drew there, the first one, is that cis or trans? This one is trans. I'm trying to show that chlorine is above the ring and this methyl group is below. And then over here I brought them both down, and so this would be the cis.
Why did we say it would be a triangle?
Because cyclopropane, mom eats pickled, 3 carbons in a ring. Cyclopropane is 3 carbons in a ring, which makes a triangle. If you wanted to do the, it'd be carbons like this. And then this guy would have a CH3. If I'm drawing the cis version, cis isomer, I'd put the chlorine down here, and this is going to have a hydrogen on it, and this is going to have hydrogen on it, and another hydrogen there, and then this guy's going to have a hydrogen. Now, really, one of these guys would be pointing down. But again, we're not going for 3-dimensionally accurate here. Yes?
For the cis, you can put the chlorine and the methyl group pointing up.
You could, yeah. There are many, many ways that you can draw these, and so that can be a little, oh, that's not very good. That can be a little confusing to students because your drawing might look different, and yet it can still be correct. I could put the chlorine here, and I could put the methyl over there. It's the same thing. So imagine this molecule, and the different drawings are just a different perspective on the same molecule. And so you have to have some spatial visualization of these models. Any other questions? Yes?
draw them on the inside?
We usually do not draw them on the inside because the geometry of the carbons is such that they never point to the inside. Like on this one, they're not pointing exactly straight up and down either. But again, we're not concerned with absolute bond angles or anything in these pictures. Any other questions?